Basically wanted us to come up with a cosine ratio. So it said the cosine, so the cosine of the sine inverse of x. Now remember, this is an inverse trig function right here. That means what we're going to plug into this is a ratio. What comes out of this is an angle, and then we're trying to find the cosine of that angle. So the final answer to this is going to be a ratio. You guys ready to go there? Thanks.
Oh, sorry.
Okay. So the final answer to this needs to be a ratio. It's very similar to this right here. That's the tangent of the cosine inverse of that ratio. So you can draw a picture from that cosine ratio and then just find the tangent ratio from that picture. So that's what we're going to do here. Everybody ready? If this needs to be a ratio, we made that a ratio by making it over 1. That means this is the opposite side and this is the hypotenuse. So all I'm going to do is I'm going to draw a triangle in quadrants 1 or 4, because remember the range for sine inverse is from -90 to 90. So I'm going to draw it right here. It doesn't say whether the opposite side is positive or negative, so it doesn't really matter where we draw it. I'm going to draw it here, with that being x, and that's 1. Now, I need the cosine ratio, so that means I need the adjacent side over the opposite, over the hypotenuse. So I need to find out how long this is right here. So using the Pythagorean theorem, this is going to be big square root 1 minus x squared. Is that all right? I think we did this a couple times before. Okay, so that really takes care of this stuff right here. I've drawn a picture that represents the sine inverse of x. What do I want from this? I want the cosine. So the cosine would be the opposite, or excuse me, the adjacent side over the hypotenuse. So that's going to be radical 1 minus x squared over 1. Or the easiest way to write this would just be radical 1 minus x squared. That's the answer. So the cosine of the sine inverse of x is square root 1 minus x squared. Seems weird, but that's what it is. We plugged in a ratio. It gave us an angle, or at least a picture of what that angle would look like. And then we find the cosine ratio, and it's just square root 1 minus x squared. That's it. I think you've got one problem like that. The rest usually have numbers. Okay? All right. Everybody good there? Okay. Those of you that are going to take calculus, that'll really come in handy. I'd keep that in mind. And then you should also read example 9 from this section. That's pretty helpful. I think it goes right along with that. So let's go to 4.2. Let's take a look at this. This section is on basic sine, cosine, and tangent equations. So like in most of math, we throw some equations in there, start solving those. We've done graphing, we've done verifying identities, we've talked about how trig functions work in general, solved some problems with those. Well, now we're going to solve equations that have trig functions in them. So if I were solving this one right here, there's a couple different ways I could do this. But probably the most straightforward way to solve x squared equals 16 would be to do what? Take the square root. Okay? Take the square root of both sides. I get an x over here. When we take the square root of something, we have to account for the fact that it could have been positive or negative, so that'd be plus or minus 4. Let's see. If I were going to solve this one, ideas there? Yeah, usually we take advantage of the zero property of multiplication. We set this equal to 0. It doesn't really do us any good to know that x squared plus 2x equals 3. But if I can set this equal to 0, and then if I can turn it into multiplication, then I'm really moving. Because, let's see, I need numbers that multiply to be -3 that combine to be positive 2. Let's see, so positive 3 and -1. And then I'd set each one of these equal to 0. That produces a -3 for a solution here, and produces a positive 1 for a solution there. And then, of course, if we plug that in, we'd have to work in the equation in order to make it true. We'd want to be aware of domain issues and stuff like that, but we don't end up with anything weird here. Okay, if I were solving this one, cube root of x equals -2. Cube both sides. Cube here, cube here. Now we get these two undo each other, so we get a plain old x on this side. We get negative 8 here. Okay? And in fact, isn't that the only answer to this one? We don't have a plus or minus or anything like that when we have odd roots. Okay? All right, and then let's take a look at this one. ln of x equals 5. 1050?
5 to the e.
Other way around?
E to the 5.
E to the 5. So you can either change this and write this in exponential form, or you can just realize what's the inverse of ln? E. So I can do e to this side and e to that side. I can exponentiate both sides. That's the word for that. E to the ln of x. This function is exponential base e. This is log base e, so they undo each other. And on this side I have e to the 5th. That's the exact answer. We could just leave it like that. If you threw that into your calculator, it's a pretty big number. All right. Any questions? Okay, one way or the other, each one of these equations was solved using an inverse. Even right here, we solved this by undoing adding 3, by subtracting 3 from both sides of the equation and that sort of thing. So that's how we're going to solve basic trig equations. We're going to use inverses. So I think we looked at some problems like this before. We're going to solve sine of x equals 1/2. We're going to do a bunch of sines on this side. We'll do some cosine and tangent on the other side of the notes. But we want to keep in mind this. There are several different ways that we can solve this, and you want to be aware of all 3 of them. So that's what we're going to talk about over here. Okay? We can use a reference triangle, or we might have to use more than one. Okay? So we can draw a triangle and figure it out from that. Okay? We can graph the trig function and the constant. So I could graph sine of x and I could graph the line y equals 1/2. It's just a horizontal line. See where they intersect or where they cross. Okay? And then we can also use a calculator. Always nice when we're able to do that. But you do have to be really careful with a calculator because your calculator is pretty dumb. All it does is spit out an answer to whatever you type in there. Okay? When you type in the square root of 16 for solving this problem right here, it wouldn't tell you -4. It would only give you the +4. You've got to figure out, oh, I put the square root in the problem. It could have been +4 or -4. So your calculator doesn't tell you everything. So you've got to be aware of that. Now, what I want you to notice here is, unlike the other problems on the notes here and in your homework, it's going to give you pretty specific directions on how they want you to write the answer and how many of the answers they want. Okay? So it's not very specific. So generally speaking, the best thing to do is to go through and solve for all of the answers. Okay? All right. So let's run through and solve this. I'm going to solve this. Let's see. Let's use the first method. Okay? Let's draw a reference triangle. So I'm going to draw a picture of what this looks like. Let's see. I need a y-coordinate of 1/2 on the unit circle. So that's going to be 1/2 right here. That would make this radical 3/2. That one's 1. How big is this angle right here? It's 30 degrees. That's the small side on the 30, 60, 90. Let's answer in radians just for the heck of it, okay? It didn't specify. So this answer right here is pi6. Is that the only answer? It's not the only answer. Okay? Now you might be thinking of another one, but if this was on the unit circle, couldn't I find another one that's coterminal with that? Like instead of stopping at pi6, couldn't I go around again? And let's see, that would be 2 pi plus pi6, so that would be 13 pi6. And then I could go around again and again and again. In fact, I could have gone counterclockwise and gotten an answer of, that would be -7 pi6. Don't those all end in the same place? They do. Okay, now we're going to clean this up just a little bit. Here's how we're going to write this down. Instead of writing all of these, because there's an infinite number of those, depending on how many times you want to go around the circle, we could say this. One of the answers is pi6 plus, then we'll just say how often it repeats, 2k pi. Does that make sense? Okay, does that cover all the solutions to that equation right there? I see a couple shaking heads going this way and some saying no, it's not. Yes or no? Nope. Nope. We just focused on this one right here. I'm going to change colors here. Could I draw another reference triangle on the unit circle that has a y-coordinate of 1/2? And if so, where would it be? In quadrant 2. I can draw this one over here. Okay, so just pretend like that's on the circle. So that's 1/2. This is 1. That's negative radical 3/2. We don't really care about the adjacent side. It's not involved in the ratio we're after. So this one would be, well, let's see, the reference triangles, or the reference angles the same side. That's pi 6. So over here, this is going to be 5 pi 6. And then I could go either clockwise or counterclockwise, full circles, and still end up in exactly the same coterminal position. So another set of answers would be 5 pi 6 plus 2k pi. Now, that covers all of them. That covers all the possibilities. Because if I were to draw a triangle down below here, it would have a y-coordinate that would be negative. So clearly that would not be a solution to this equation. This is all of them right there. Any questions? So we've got this answer that repeats every 2 pi, and this answer that repeats every 2 pi. Okay, and we solved that using reference triangles. David?
How again did you know that the angle that flipped over the y-axis again?
Because the y-coordinate needs to be positive 1/2. It's positive 1/2 over here. If I draw the same triangle over on this side of the y-axis, the y-coordinate is still positive.
So, yeah,
Yep. Everybody good there? Okay. Let's solve it using this technique. Let's look at a graph, and maybe we can see why these repeat every 2k pi. So I'm going to draw, let's see, it's a sine graph, right? So the sine starts here, goes up like that. So it's going to look like this on this side. Okay. That's not very good, but we can deal with it. Looks like that. And we want to know where it equals 1/2. Y equals 1/2. So 1/2 would be a line that runs about right in there, right? So guess what that answer is right there? Pi 6. So it intersects that line going on the way up. It does it again going up here. Does it going here. Guess how far it is from this one over to that one right there? Shouldn't really be a guess, should it? Because we know the period of this function. It repeats the same cycle every 2 pi units. So to go from this one to the next one that occurs in the same fashion should be 2 pi units. So if this is pi 6, this one would be 2 pi units away. That would be minus 2 pi units away, and it would repeat every 2 pi. So that's why we write the 2k pi. Remember, k can be any integer. Questions there? And then we've got this guy right here. If this is pi, there's our 5 pi 6. Now it's pretty tough to tell on a graph exactly where it would cross. We're kind of relying on our knowledge that we gained up here. But there's this answer, and then it repeats over here, it repeats over here, and guess how far it is between here and here? 2 pi. Okay? So you can see why those repeat. You can see that there are two answers that hit 1/2 in between 0 and pi, and you can see how often they repeat. Okay, are there any questions? Okay, grab your calculator. And for this, we'll probably think of this in, degree mode's probably easier since recognizing pi 6 is kind of tough to do. So here's what we'll do on this. If it's the sine, if it's the sine of x equals 1/2, we're going to do the sine inverse of this side and the sine inverse of this side. So that's going to be x equals, and then we'll just type this into our calculator and it's going to spit out an answer. So we're going to put this in degree mode just so it's easier to find. There we go. Let's check the mode. We're in degree mode, and I'm going to type in sine inverse of 0.5. And it says 30 degrees. Okay, now here's what you've got to keep in mind. Okay, when you solve this on a calculator, it will only give you one answer between negative 90 and 90, because that's the range for sine inverse. So it's telling us that the answer is 30 degrees or pi 6. It gives us this one right here. So here's the way I like to diagram these. Okay? If it's a sine inverse, your calculator will give you this, and I'm going to change colors. Your brain has to figure out this answer over here. Just like your calculator will tell you that the square root of 16 is 4, you had to know, your brain had to figure out that we needed to put the plus or minus on there. The other diagram that would look exactly the same as this one that the calculator produces would be over here. You can kind of take this side, quadrant 4 and 1, and just flop it over the y-axis. Okay? So if that's 30 degrees, this is going to be 30 degrees. That makes this 150 degrees, or that would be our 5 pi 6. Okay? All right. Any questions there? Kind of a long problem. We looked at it in 3 different ways. We ought to talk about the kind of the shortfalls or the limitations of each one of those techniques. So the first one is this. You may not be able to find the answer using triangles unless it's a common angle. Now this one was. The ratio is 1/2. We see that ratio all the time. It's stuff that we memorized from chapter 1. If the ratio had been 3/4, you wouldn't have been able to figure out exactly what it was, no matter how nice your picture was. You'd have to use a calculator or some other technique. Okay? It's difficult to use the graph to get exact answers. We knew what these points were where they crossed because we had already drawn a picture. So these triangles are really helpful. And a calculator is really helpful, but you've got to be aware that your calculator is only going to give you one answer. And there might be tons of answers. Here we came up with an infinite number of answers. Your calculator cannot do this for you. You have to know that. You've got to use your brain to figure that stuff out. Okay? So each one of those techniques has its limitation. If I had to say, I like this one the best. Kind of incorporates them all. You can kind of see the period. You know, you've got to go around the circle, you know, one full circle in order to hit that coterminal point again. Okay, are there any questions there? Okay. Now, this first example, it's a repeat, so I've got this as 1 star. This is pretty specific. It has instructions like the ones that you're going to see on the assignment. It says, give all the real solutions. Now, when it says all, that's your clue that you're going to have a k in the answer somewhere. And when it says real, that's your clue that it's going to be probably in radians. Well, it is going to be in radians. It's probably going to have a pi on it. So if the instructions for that particular problem had been this right here, your answers would have been x equals pi 6 plus 2k pi, and x equals 5 pi 6 plus 2k pi. If the instructions say give all real answers, you're giving basically answer sets. If the instructions tell you an interval where you need to find the answers. So we want to find the answers between just 0 and 2 pi. 0 included, 2 pi not included. So we could draw a picture like this, and it's only this answer as we go around the circle, and this answer as we go around the circle. Or you could look at this and say, look, if I plug a 0 in for this, in for k, then one of my solutions is pi 6. What if I plug a 1 in for k? What answer would that give me? 2 pi plus pi 6, 13 pi 6. What's wrong with that according to these instructions? It's outside of the interval. It's a little bit too big. Okay? So there's one of the answers. And likewise, if you plugged in a -1 or any negative number, it's going to be outside that interval. Okay? So if I plugged a 0 in here, the other answer that I get is 5 pi 6. If I plugged in anything 1 or bigger, or -1 or smaller, again, it's going to produce an answer that's outside the interval. Okay. Any questions? Okay. And then this last one just says, solve that exact same equation, but write the answer between -90 and 90. How many answers do we get there? We only get one. We get this one right here that our calculator gave us, this one right here that we figured out using a triangle, and hidden in there are how they want us to write it. They want us to write this in degrees. So on this one, we'd say x equals 30 degrees. Okay? So not only is the function important, but the instructions to solve the problem are important because it's going to be different for each problem set. Okay, any questions there? Sure? All right. Okay, let's take a look at these next couple of problems on this page, and then we'll do some that involve cosine inverse and tangent inverse. It says, find all the real solutions. We're going to be using pi, and we're going to be using k, because we're going to be writing down answer sets. So I'm going to draw a picture for this one, just because I like that better. I want a y-coordinate. Let's see, I want a y-coordinate that's 0. That only happens here. And where? On the other side, right? So this is going to be x equals 0 plus. Now, how often does this one repeat? Okay. If you stick with the way we did it up above, and you don't have to write this if you don't want to, 2k pi. And then this one over here would be x equals, this would be pi plus 2k pi. You could write your answer like that, but that would be a little bit on the silly side. Can somebody tell me why? Because it repeats every pi. Why not just say, hey, you know what? I'm going to start with this answer, and to get to my next one, I do pi units this way, another pi, another pi, another pi. So we could combine the two of these, and we could say x equals k pi. Because if you plugged in a 0, you get that answer right there, you get 0. If you plug in a 1, you get pi. If you plug in a 2, you get 2 pi. If you plug in a negative 1, you get negative pi, which lands on that point right there. Does that make sense? Okay, watch. You don't have to write this down. If I graphed that function and I graphed the line y equals 0, it hits right here, right here, right here, right here. How far is it between each one of those places where it crosses the midline, the center line? It's pi units. Okay, so it makes sense why this one repeats every pi units and the other one repeats every 2 pi units. Okay, all right. Questions? Okay, let's take a look at this one here. I'm going to solve this one using a picture because this one's easy to solve using a picture. There's what the graph looks like, and I want to know when this function equals 1. Hits at the top here, at the top here, at the top here. What is that x-coordinate? Pi halves. So this would be x equals pi halves. Okay, give it a starting point. Any one of these would do. This is the one that makes the most sense. And then how far is it in between here and here? And in fact, every one of those peaks of this sinusoidal graph. 2 pi. So this is going to be 2k pi. There's our answer. If you wanted to draw a picture of this using triangles, this is 1 over 1. So that would be 0 here, 1 here, and 1 here. So we're straight up and down. And the only way to get back there is to go around an entire full circle either direction. Or 8 full circles either direction. Or 42 full circles either direction. Okay? So start at pi halves, tell it how often it repeats. In this case, it's 2k pi. Questions there? Okay, would you solve this one and write down all the answers in degrees? Don't care how you do it. If you want to use your calculator, that's fine. If you want to graph it, that's fine. If you want to think of the unit circle and draw triangles, that's okay. Go ahead and do that one, please. If that's not familiar enough, you can write it like that. Got it? Think you got it? Check with your neighbor. See if they got the same thing. Okay, so I'm going to solve this one using the calculator first. Okay, we've done triangles, we've looked at graphs. So if I were going to do this on the calculator, I'd just type in sine inverse, and then I'll just type it in as it was originally, 1 over radical 2. It spits out an answer of 45. Now that's all it spits out, and yet the problem says we want all the answers in degrees. That's in degrees, we're in good shape there. So the answer is x equals 45. Well, how do we write down the rest of them? Okay. So this would be plus 360k. Now, is that the only answer? It's not, because remember, I said your calculator, if you're doing sine inverse, your calculator is going to give you this answer right here. It gave us 45 degrees. We have to realize that there's another reference triangle on the other side of the y-axis that has exactly the same sine ratio. So that would be over here, 135. So your calculator gives you the 45. You've got to use your brain to figure out the 135. So the other answer set is 135 plus. How often does that one repeat? Every 360 degrees, because you'd have to go all the way around a full circle in the clockwise or counterclockwise direction to get in the same place. Any questions there? Okay. Those two answer sets are the solution. Okay, so make sure you pay attention to the instructions. Does it want only a couple answers within an interval? Does it want them all? Does it want it in radians? Does it want it in degrees? What does it want? Okay, any questions? Okay, this other side is basically the same stuff then. It's just using cosine and tangent. You can solve equations using cosecant and secant and cotangent. We just don't see those as often. Okay, and if we did, we'd probably change them into a cosine, a tangent, and a sine anyway. So it says find the solutions of this on 0 to 360. So we only have to find the ones in that particular interval. And we know we've got to do it in degrees, so we're probably more comfortable with degrees. Let's do this. I'm going to draw a triangle for this one. I need a cosine ratio, or in other words, an x-coordinate of negative radical 3 over 2. So if this is negative, radical 3 over 2, that's 1 and that's 1/2. That gives me a picture of one of the solutions. That would be, I already did this earlier, 150. Okay? But there's another triangle with exactly the same x-coordinate down below here. So that would look like this. And if this was 150, let's see, how could we figure out the other one? So the first answer is 150 degrees. We know that for a fact. Where is this one? It's at 210. Okay. Now, you can go through a bunch of formulas to figure out, all right, if it's in this quadrant and here's my reference angle and all that sort of stuff, do I add to 180, subtract from 180, add to 360, subtract from 360, all that sort of stuff? Okay. That's why a picture is so helpful. If this is 150 degrees, that's going to be 150 degrees. So I just take 360 and back off by 150 degrees. 360 minus 150 would be 210. Or if that's a 30-degree reference triangle, that's 30 degrees, so I can take 180 and add 30 degrees. That would put me at 210 also. Okay? Pretty easy, right? Okay. Let's take a look at the next couple. It says, find all the real solutions for cosine of x equals -1 and cosine of x equals 1/2. So all real. That means we're going to have answer sets. They're going to have k's in them, and they're going to be done in radians. So I need the x-coordinate to be -1. That only happens in one place, right here. That's the only place it happens. If you do cosine inverse of -1, your calculator will tell you 180 degrees, which we know is pi. And then how often would this repeat? Is this like sine where we can come over here and get the same x-coordinate? It's not. So how often does that repeat? Yep. 2k pi. You don't have to draw this, but you could at least think of what this would look like. Cosine looks like this. And we want to know where it hits -1. Right here at pi, over here at 3 pi, back here at -pi, back here at -3 pi, and so forth. So you can kind of see, based on the graph, how often it would repeat and why that is the answer set. And it doesn't hit -1 in any other place. Okay? All right. I'm going to solve this one using the calculator. So let's take a good look at this. What I'm going to type into the calculator is cosine inverse of 1/2, right? So we'll do cosine inverse of 0.5. And it says the answer is 60. Answer 60. So I'm going to draw that right here. 60 degrees. Your calculator gives you this. Your brain's got to figure out not only how often it repeats, but it's got to figure out that you can have the same triangle down below with the same x-coordinate of 1/2. So if the only thing your calculator spit out was the 60 degrees, how do you write the answers for this problem given the instructions? Go ahead and write down what you think the answer is. Check with your neighbor, see if you got it right. If you're going to rely on your calculator, you've got to make sure that you know how to interpret its answer and get all the other stuff that goes with it. Okay, how many answer sets? 1 or 2? 2 answer sets. The first one is x equals pi thirds, I heard it. 2k pi. It repeats every 2 pi units. There's one answer. And the one down here would be x equals 5 pi thirds, right? Because this would be 300 degrees, which is 5 pi thirds. So 5 pi thirds, and how often does it repeat? 2k pi. So there are the answers. Now, if you looked at your neighbor's paper and they said -pi thirds plus 2k pi, is that okay? Sure, because that represents this one right here. It's not as standard. Usually it's best to start out with a positive angle and then say how often it repeats, but that would be okay. Much prefer the 2 of those, and if it were a multiple choice question on a test, it would be one of those 2. It probably wouldn't have the -pi thirds. Did you have a question?
Yeah, could you use degrees instead of plus 2k?
On this problem, can you use degrees? No, okay, because it said real. Whenever it says real numbers, you want to answer in radians, okay? All right, any questions? Easy enough? Okay, sine and cosine are not too bad. We know their graphs really well. The coordinates, those ratios show up on the unit circle and all that sort of stuff, so they're pretty easy. If we take a look at tangent, it's a little bit different, and here's the first difference we want to point out. Sine and cosine both have periods of 2 pi. What about tangent? Tangent is just pi. So we know right away there's going to be something different. So let's solve this one right here, and this is why I'm a big fan of thinking about this in terms of both a graph of the triangle and a graph of the trig function. So let's do this one right here. Let's do tangent of x equals 1 over radical 3. If this is a tangent ratio, that means this is the opposite and this is the adjacent, right? So if I draw a picture of that, and notice it says all the real solutions, then it would look like this. The opposite side is 1. The adjacent side is radical 3. That makes this 2. If you use the Pythagorean theorem, or if you've got that memorized, which, my gosh, I hope you do. How big is this reference angle right here? It's 30 degrees, or because it said real, we're going to think of this as, well, that's pi 6. Now, before you say, gosh, I'd have to go all the way around the circle again to find another one that has exactly the same ratio, keep in mind that the tangent is the ratio of the y-coordinate over the x-coordinate. And right here, it's positive. Remember, there are two places where each of those trig functions is positive and where they're negative. Tangent, this could also have been -1 over negative radical 3. So couldn't I draw a picture over here where this is -1 and this is negative radical 3, and that's 2. And that still has a tangent ratio of 1 over radical 3. So if this is pi 6, what's this one over here? Well, this little angle right here would be pi 6, so that would be pi plus pi 6, so that would be 7 pi 6, right? So do we write down another answer? Don't write this down. Do we write down another answer of 7 pi 6 and then say how often that repeats? We don't. And this is what's unique about tangent, and we're going to look at why it works this way in just a second. These are straight across from each other, okay? They're symmetric about the origin. They're 180 degrees apart. So if I know where this one is, how far is this one from it? Pi. Pi. So the answer on this problem is x equals pi 6 plus k pi. Now, why does it work that way? Again, you don't have to graph this, but you could just watch. There's one cycle with the asymptotes. Here's another cycle with the asymptote. Here's another cycle with the asymptote. And we want, this is roughly a half. So if I draw what that line looks like, it intersects here, here, here. How far are those in between each place where they intersect? Pi, because that's the period. Okay, so there's the answer. So let's do the next one. Tangent of x equals 1. If I draw a picture for this, remember that's the opposite over the adjacent, 1 over 1. This would be radical 2. You don't even have to do that because if you know the legs are the same, then you know it's got to be a 45, 45, 90. So that's 45 degrees or pi fourths, and then there's another one down here that looks exactly the same. So the answer is pi fourths plus k pi. Any questions? Sure? Okay. Let's see. Could we solve this one just by looking at what we've got on the board right now? It hits 0 right here. It hits 0 right here, and so forth. So where's the first place it hits 0? At 0. And how often does that repeat? Just like the other ones. So this is going to be, instead of writing 0 plus k pi, it probably would be best to just write x equals k pi. Call it good there. Okay. Any questions on that? Okay. Then let's take it. You're sure? These are pretty easy? Okay. Let's take a look at the last couple problems. And really, it's just these 5. These last couple are going to get us ready for the last 2 sections in this chapter. It says, solve the following equations. So we want to solve this on this interval right here. So we only have to get answers between 0 and 2 pi. We know they've got to be in radians. And like any other equation, we're going to solve this by getting the variable by itself. So if this were 2 square root x plus radical 2 equals 0, everybody here would know what to do. Move the radical 2 over, then divide by 2. Well, we do exactly the same thing here. So we're going to move the radical 2 to the other side by subtracting. So this is going to be 2 sine alpha equals negative radical 2. Divide everything by 2. So I get the sine of alpha equals negative radical 2 over 2. You can draw a picture of that. You can use your calculator. You could draw a graph. graph the sine function and graph radical 2 over the line radical 2 over 2. Again, that's not quite as accurate, so I would advise one of the two of those. I'm going to solve this one by drawing a picture. I need a y-coordinate of negative radical 2 over 2. That happens here and here. And what size are those reference triangles? 45 degrees, right? So that makes this one 5 pi fourths, and that makes this one 7 pi fourths. And do I need to worry about answer sets? Do I need to write down 2k pi or anything like that? Why not? Yeah, because it only said, hey, start here and go around the circle and find me a couple angles that have sine ratios of negative radical 2 over 2. So the answer on this one, 5 pi fourths and 7 pi fourths. Questions? All right, look at the next one, please. So if you were like, if the calculator doesn't work all the time and it only gives me one answer and I've got to use my brain for the rest of it, I'm just going to stick with the other two methods. This is why you can't do that. You will have problems like this. It says, solve this trig equation on this interval. Okay, now, this can be a struggle because this is certainly not a ratio I recognize. And you have to use your calculator to figure this out. And your calculator gives you answers in radians that are really ugly looking. They're just decimal numbers. Okay? So let's think about this for just a second. It might be helpful to at least think of a picture that would look like this. If I put that over 1, that means the adjacent side is pretty darn big in comparison with the hypotenuse. That means we're looking for an answer where this is 0.873 and that's 1. So we're looking for a pretty small decimal number to come out of our calculator. Remember, our calculator is going to give us answers up here because we're using cosine inverse. And then we've got to use our brain to figure out this stuff down here. So let's go ahead and grab the calculator. And let's do, I'll just recall that. And it is 0.873. Is that right? See some shaking heads. Anybody want to say no? What's wrong? It's in degrees. So I come back here, change the mode. I'm going to switch this to radians. We have to answer this in radians. It gave us the interval. So I'm going to hit second quit. The cool thing is I could just type enter, or I could recall that really quickly. There's my small decimal number for the radian measure. So that means this answer right here is 0.059. So I'm just going to do 0.51. Is everybody okay with that? So this is 0.51. That's my first answer. So x equals 0.51. If I just did that one, how often does it repeat? 2k pi. Do I need to worry about repeating things outside the interval from 0 to 2 pi? Not on this one. Okay, so I've got one of the answers. And then I've got to use my brain to figure this stuff out right here. There's another one right down here. Let's see. If that one is 0.51, what's this one right here? So here's what I've got. I've got this angle right up here that's 0.51. I need the same one, same size reference angle, but I need it down here in quadrant 4. If that's 0.51, the question is, we change colors here. What's that angle right there? It's not quite 2 pi. How much do we have to back off from 2 pi? 0.51. So we're going to take 2 pi and we're going to subtract 0.51. So the other answer on this problem is, you could actually just write it like that, or let's throw this into the calculator. I'm going to do 2 pi minus that last answer there. So 5.77. Does that look like about 5.77? If all the way around the circle is 2 pi, or what would that be in degrees? Or sorry, not in degrees, in decimals? 6.28. That's a little bit shy of 6.28. That looks pretty reasonable, right? Again, your brain's got to figure this stuff out. Okay, you cannot solve all these on your calculator. Good? Okay, do the last one, please. See a couple shaking heads. That's good. Domain issue, right? Okay, think about this. Graph cosine and graph this line right here. Cosine looks like this. Gets up as high as 1 and as low as -1. And if I were to graph that right there, this would be y equals 1.873. Do they ever touch? Do they ever cross? Nope. So there is no solution. Okay? That's too big a ratio to plug into cosine inverse. And it's outside the range of cosine, so there's no way they're going to cross. Okay. Now, there are two more problems similar to ones on your assignment. They're just basically solving equations. Here's the nice part. You're solving for whatever variable they tell you. Okay? So all we're going to use is inverse functions to solve these. We want to get the m by itself. Think of that as being underneath the square root. If that were the case, the first thing we'd do is we'd move the 2 to the other side. How would we do that? By subtracting. So this is t minus 2 equals -6 times the sine of m. I need to get the m by itself, so I'm going to get rid of the -6. So here's what I've got. T minus 2 over -6, and if you want to distribute the negative through on the top, that's fine with me, equals the sine of m. And how do I finally get the m completely by itself? How do I get it away from the sine? Sine inverse. Not times the sine by take the sine of both sides. So we're going to do, take the sine inverse of both sides. So sine inverse of this side, sine inverse of that side. So I get m equals the sine inverse of t minus 2 over -6. If you wrote it this way, 2 minus t over 6, that'd be fine. That one's fine with me. Okay, any questions? Okay, let's look at part B here, because you're going to have some problems to do like this shortly. We want to get b by itself, beta by itself. So that's going to be the sine of beta is equal to 52.9 sine of 9.7 degrees over 15.9. So that means beta is going to be sine inverse 52.9 sine of 9.7 all over 15.9. And before I reach for my calculator, what am I going to do? Or at least what am I going to think? What's that? Oh, you're right. It's 15.4. Thanks. What did you say, David?
Everything's not in the same terms. You got degrees.
No, these are okay. These are just measurements. Okay. Make sure your calculator's in degrees. And what else do you notice about this problem right here in the instructions? Where it wants answers. Where does it want answers? In quadrant 1. In fact, that's a quadrant your calculator's going to spit out, and we don't have to worry about anything else. So we're going to type this into the calculator after making sure that we're in degrees. So we'll do sine inverse 52.9 times the sine of 9.7. Okay, do I need parentheses around the entire top? It's not a bad idea, but on this one it's all multiplication and division. Okay, so we'd be fine on that one. So then we're just going to divide by 15.4. And if I type this incorrectly, 35.36. Okay. Is that the answer? David?
Yep.
That's the answer in degrees. We can solve the equation in degrees, but it wanted the answer in radians. So we just take that and quickly convert it. So we're going to multiply this by pi over 180, and that will be the answer in radians. Okay? The point there is you can solve something that looks like a pretty complicated equation. Just make sure you write the answer in the right format. Okay. I'd like you to solve these 3 problems before you come to class next time. If you don't know how to solve those, please come see me before class next time. Okay? All right. Thanks.